In this video, we're going to have a look at finding the eigenvalues and the eigenvectors of this 3x3 matrix. I know a lot of students struggle with this, so I'm broken it down into two main steps that you want to focus on remembering, and everything else sort of fits together like a puzzle. So first of all, it tells us to find the determinant of a minus lambda I and make that equal to 0. So what is lambda I? Well, for a 3x3 matrix, the identity matrix is 1 along the diagonals and 0 everywhere else. So I'm just going to write that out very quickly. In that case, lambda is just a scalar, meaning you can treat it as if it's a whole number like 2. In that case, you just multiply it to every term that's inside of this identity matrix. So 1 times lambda is lambda, 1 times lambda here would also be lambda, and 1 times lambda here would also be lambda. All these terms remain as 0 because 0 times lambda would always be 0. It tells us to put it in the form a minus lambda I. Now, a minus lambda I, what you do for that is you take the matrix for a, which I'm just going to write out one more time. 4, 0, 1, minus 1, minus 6, minus 2, 5, 0, 0. And you take away from that the matrix that we just formed, the lambda times the identity matrix. So I'm just going to very quickly write that out one more time. Now, when you're subtracting matrices, it's honestly not too difficult. You can do 4 take away lambda, and that gets you the number on the top left. You can do minus 1 take away 0, which is minus 1. 5 take away 0, which is 5. And then you can do that again and again for each term inside of the matrix. So 0 take away 0 is 0. Minus 6 take away, I'm on the right one, yeah. Minus 6 take away this middle term lambda is minus 6 minus lambda. And I'm just going to fill the rest in just like so. So 0 take away 0 is 0. 1 take away 0 is 1. Minus 2 take away 0 is minus 2. And then 0 take away lambda is minus lambda. To find the determinant of a 3x3 matrix, what you do is you take the number on the term on the top left. So by the way, we're defining the determinant now and making it equal to 0, which is this step here. So I might as well do it here actually. So we write out 4 minus lambda and then the determinant of this 2x2 matrix. So let's write that out. Minus 6 minus lambda, minus 2, 0 minus lambda. And then take away the value here in the first row, second column, so 0, lots of, well, we don't even need to include anything here. Technically, we would write minus 1, minus 2, 5, minus lambda in this matrix, but 0 times anything is always 0, so I wouldn't even bother wasting time with that. I'll just write minus 0, and then plus 1 lots of the determinant of this section, which is minus 1, minus 6 minus lambda. If you'd like me to make a separate video about the determinant of a 3x3 matrix, just let me know in the comments and I'll do that. I think I have made one in my channel though, so try to look out for it. So when you're finding the determinant of a matrix, it's AD minus BC, meaning this term times this term, take away this term times this term. And we're multiplying all of that by 4 minus lambda, so I'm just going to write this out just like so. 4 minus lambda, and then a big bracket to multiply these two together. So minus 6 times minus lambda is positive 6 lambda. Minus lambda times minus lambda is plus lambda squared. We take away from that minus 2 times 0, which is 0. So I'm not even going to include actually. We can close the bracket. And then we take away 0. And then we add 1 lots of, well, minus 1 times 0 is 0. Take away 5 lots of this term here. Minus 6 minus lambda. Now minus 5 times minus 6 is positive 30. Minus 5 times minus lambda is plus 5 lambda. So we can replace everything in the bracket now with 30 plus 5 lambda. So I'm just going to very quickly do that. 30 plus 5 lambda. And now we can multiply the brackets. So 4 times 6 lambda is 24 lambda. I'm saying that quite low here, lambda. But 4 times lambda squared is plus 4 lambda squared. Minus lambda times 6 lambda. So I'm just going to double check I'm doing everything correct. Yes, it seems I am. Minus 6 lambda squared. And then minus lambda times lambda cubed squared now gets you to minus lambda cubed. So we're going to go to the cubic terms here. And then plus 30 plus 5 lambda all equals 0, because remember we're putting it into the expression that the determinant of all this matrix that we formed is equal to 0. So equals 0. Let's do the rest somewhere here. Collecting like terms now, we have minus lambda cubed for the only cube term. So minus lambda cubed. And then comparing the terms of the squares of lambda. 4 lambda squared take away 6 lambda squared is minus 2 lambda squared. Now the coefficients of lambda, 24 lambda plus 5 lambda is 29 lambda. And lastly, we have the 30. So plus 30 all equals 0. Okay, so where do we go from here? Well, we have to solve for lambda, and because it's a cubic function, you'll get that there's 3 roots of lambda. And that means, by the way, solving for lambda is what gets you the eigenvalues. These are the values that we're looking for in this case. So what I'm going to do is I'm going to erase some of this here, just so we have space to do this whole division. Now, one thing I would advise is you multiply each individual term by -1. That gets you to lambda cubed plus 2 lambda squared minus 29 lambda minus 30 equals 0, and it makes it a lot easier to solve. Now, what I've noticed from doing this question beforehand is that when you replace lambda with -1, that makes this whole expression equal 0. Using what we know about the factor theorem, that means that lambda plus 1 is a root of this cubic. What we can now do is divide the whole cubic, which I'm just going to write out here. Lambda cubed plus 2 lambda squared minus 29 lambda minus 30. And we can divide it all by lambda plus 1. So let's do that. But actually, what I'm going to do is I'm going to transport all of this here and divide. Because it's going to take a little bit of space, this factor theorem. If you already know how to do this, you can just skip ahead a little bit. But to go from lambda to lambda cubed, you have to multiply by lambda squared. Lambda squared times lambda is lambda cubed. Lambda squared times 1 is plus lambda squared. We take away everything. We can cancel out the cubic terms. And then 2 lambda squared take away lambda squared is 1 lambda squared. We carry on the minus 29 lambda and then we repeat the process. So this time to go from lambda to lambda squared, we add lambda. And then lambda times lambda is lambda squared. Lambda times 1 is plus lambda. Take away again. Minus 29, take away 1 lambda is minus 30 lambda. And then we pull down the minus 30. Lastly, to go from lambda to minus 30 lambda, you multiply by minus 30. And what you'll see is that when you multiply by minus 30, everything here will end up equaling 0. Because minus 30 times lambda is minus 30 lambda. And minus 30 times 1 is minus 30. And that all cancels out to 0. That means that you can write this cubic in the form of lambda plus 1 all multiplied by this quadratic here. Now in this quadratic, you can simplify this into, what can you simplify into? Lambda plus 6, lambda minus 5. And from there, you've got your cubic factorization. And in order to make that equal to 0, once you do that, you'll get the 3 eigenvalues. Either lambda 1 is equal to -1, lambda 2 is equal to -6. I just written like different subscripts here because they're different values of lambda. They're the different eigenvalues. And lambda 3 is equal to 5. And these are your 3 eigenvalues here. Now, pretty long process, but hopefully that all made sense to you guys. Okay, let's highlight a different color. And now we're going to go through how we can use these to find the eigenvectors. So I'm going to show you only for one example because once I show you for one, the rest of them you should be able to do. So what you do is you take the expression that you form for a minus lambda I, which is, oh sorry, I rubbed it out. But a minus lambda I, well here, it will be 4 take away lambda. But in our case, let's consider it for one eigenvalue. By the way, there's 3 different eigenvectors that come from the 3 individual eigenvalues. Let's pick out the eigenvalue of -1. And let's find the individual eigenvector for that eigenvalue. So again, we're forming a minus lambda I for our bracket, bracketed matrix. 4 take away, replacing lambda with -1. 4 take away -1 is 5. And then this would be 0, this would be 1, this would be -1. -6 take away lambda would be -6 take away -1, which is -6 plus 1, so -5. And then this would be -2, this would be 5, this would be 0, because again, 0 take away 0 is 0, 5 take away 0 is 5, and then 0 take away lambda. Now in our case, again, we're replacing lambda with -1, so it becomes plus 1. All of that multiplied by xyz is equal to 0, 0, 0. From that, we can form expressions that help us find the value of x, y, and z, the eigenvector. So how we do that is 5 times x is 5x, 0 times y is 0, and then 1 times z is z. So 5x plus z is equal to that value there, 0. This is important because if we think about it, that means that if x is equal to 1, then z would be equal to -5 because 5 take away 5 is equal to 0. So that tells you that in our eigenvector for this specific eigenvalue, we know the x value is 1, and for that the y value is, sorry, the z value is -5. We now need to think about the y value. There's no point taking this expression and multiplying it by this because we end up at the same expression. However, if we look at the middle row, minus 1 times x is minus x, minus 5 times y is minus 5y, and then that minus 2 times z is minus 2z. And that's all equal to the middle term here, 0. Now, why this is important is we can actually make z the subject of this equation. So z is equal to minus 5x, and we can replace the z in this equation with minus 5x. Once you do that, what you'll see is that minus 2 times minus 5x is positive 10x. And this helps you get an equation in terms of x's and y's. This is useful because we already have an expression for x, a numerical value of x here. And we can use y to form the y expression of that matrix. So let's do that. Minus x plus 10x is 9x. And then minus 5y is equal to 0. Add 5y to both sides, so 9x is equal to 5y. In that case, y is equal to 9 over 5x. Meaning that if x is equal to 1, y would be equal to 9 over 5 times 1, so 9 over 5. To find the better format for the eigenvector, we'd multiply each individual component by 5 so that this is no longer a fraction. So 1 times 5 is 5, 9 over 5 times 5 is 9, minus 5 times 5 is minus 25. And we've formed the expression that for this specific eigenvalue, this is the eigenvector. Quite a long process, but hopefully it made sense to you guys. This here is the next video, which do be look out for it. It's for a 2x2 matrix, but it's exactly the same process as this. Very long process. It would be a lots of marks in an exam, but you want to mainly remember these two parts that we used to do this whole expression. Everything else sort of falls into line, just like I mentioned at the start of the video. Be sure to leave a like if the video helped and subscribe. I'd appreciate a lot. Thanks for watching. Thanks for watching the video. I hope it helped. If you have any tutoring inquiries for A-level further maths, be sure to hit my website up at www.excellineducation.co.uk.